Hi, in this video, we're going to look at a special data set. And this data set gives us 4 linear models, and the linear models are almost exactly the same. But when we dig a little bit deeper, like, well, okay, so we'll have like the same correlation, we'll have the same coefficients, we'll have a lot of the statistics about the model, these 4 models are going to be the same. But when we dig deeper, we can see that these are very different data sets. And in reality, these models would perform very differently if we were to launch them, if these were real data. And so this lecture is all about motivating you to look deeper into your data. Don't just like run your code, get your model, and call it a day. The goal for today is to get you to, after you get your model built, like go in and double check things. Check to see, does your model make sense? Does it pass the sniff test? I call it the sniff test to look at, when you go back and you look at your models, look at the output, look at the residuals. Does this make sense? Does this look good? Do I trust my career on this model right here at work? Good questions to ask. All right, so this is coming from the Anscombe data set. And the Anscombe data set has 4 X predictor variable columns and 4 Y target variable columns. And the data in the code are modified from the textbook's website. Here's the website, a modern approach to regression with R. All right, so let's go ahead and start out. And so first thing I'm going to do, I'm going to load my data. I'm using read.table. Notice I've got the full file path right here. I typed out the whole thing, make it easier to read it. The data set has headers, has a header row on it. So remember that that's a row that has the column labels, but is not data itself. By default, read.table does not have a header in it. It says header equals false, which would screw everything up. So we don't want that. And I know that everything needs to be numeric. So I go ahead and set call classes to numeric. This parameter of the read.table function, what I need to do, I have 2 choices. Either I can put, for each column, I can put in what it is. So here we have case 1, 2, 3, 4, 5, 6, 7, 8. I would have a vector of length 8 here if I wanted to have, if I wanted to declare each type or each column individually. Here, I know that all of them are numeric, and what R will do, R will recycle whatever I put in. So in fact, I could have had like integer, and then numeric, and then it would have gone integer, numeric, integer, numeric, integer, numeric, and so on, all the way through. And if it's recycling, it's going to throw a warning message to let you know. In general, you either want to have just like length 1, so it does it the same thing to everything, or you want it to specify all of them. All right, so now let's go ahead and just take a look. This is a pretty small data set. It only has 11 rows, so I can go ahead and print the entire thing on the page. And the knitter package has a cable function that makes it a little bit prettier when we print in R Markdown. R Markdown is the system that I'm using to make these documents. All right, so we can see that X1 is the predictor variable for Y1, which is a target variable. X2 is the predictor variable for target variable Y2, and X3, Y3, and same thing for the 4s. Okay. Well, now let's go ahead and take a look at our data. Let's take a look at the univariate statistics. So case is just a row number. We don't really care about that. I can see that for the X's, the minimum is 4, 4, 4, then 8, 11.5, 11.5, 11.5, then, sorry, that's the 3rd quartile. For the max, we have 14, 14, 14, and then 19. Okay, so we can see that there's something definitely different going on with the X4. All right, now let's take a look at our target variables. We can see that the minimums, 4.3, 3.1, 5.4, 5.2. So there's a lot more variation here. And then the max, 10.8, 9.3, 12.7, 12.5. Okay, so that's, there's a lot more going on here. if I look at the means of the x's, we can see that they're all 9. Huh, that's interesting. You know, medians, 9 or 8 at the end. All right. First quartile, 6.5, and then an 8. Third quartile, 11.5, and then again an 8. Okay. So you'll notice that median, mean, median, mean, median, mean are all the same on the first 3, and then there's a difference between on X4. So that's a good sign that there might be some skewness or something going on. All right, let's go ahead and build the models. So I'm just going to use the LM function, which stands for linear model. And when I do this, I go ahead and specify the formula. So remember, the tilde means that this variable depends on these variables over here. If I had more than one variable on the right, I would put like a plus sign on there. And so we can just see that I'm specifying the data as the Anscombe data set. And we just go down the list and build all of our models. Nice and easy peasy, lemon squeezies. All right, so now let's go ahead and take a look at the model statistics. Let's take a look at the coefficients, the standard errors, t-values, all that. So what'll happen is you'll notice that the coefficients, standard errors, the t-values, and the p-values are all practically the same. Either they're the same or they're nearly the same for all 4 models. And then we'll also notice that the residual standard errors, degrees of freedom, both R squared and adjusted R squared, and the F-tests are practically the same for all 4 models. So if I look through here, all right, so if I look at the estimates for the coefficients, we have 3 and 0.5. We have 3 and 0.5, and it's not quite 3, but I mean, it's really close, right? 3 and 0.5. 3 and 0.5. Now, if you go through and you look and you dig in and you go line by line, you look at this, you'll notice that all of the models get practically the same, R squared of 0.66, practically the same adjusted R squared of 0.63, and then that F statistic is 18 on 1 and 9 degrees of freedom. P-value is statistically significant. Okay, and that's going to be the same for all of them. So, like so far, if all I was looking at was this output, I would see, hey, these are the same models. I wouldn't even notice what's going on. Now, something to also remember is that when we look at the residuals, you'll notice that the mean is not printed here. The mean on the residuals in a linear regression model, it's very important. This is for a linear regression model only. This is a special situation. The residuals always add up to 0. Therefore, the mean is always 0. Now let's go ahead and let's build scatter plots to take a look, and let's go a little bit deeper and let's see what's going on. Okay, so for my scatter plots, I'm just going to use the plot function. I just specify the x variable for the first model, the y variable for the first model, and I'm specifying the x and y limits to make sure that I have the same. Remember that when we looked at the univariate statistics, each of the 4 data sets had different maximums and minimums. Here, what I'm doing is I'm setting all 4 plots to the same x and y coordinate range. That way it's easier to compare them. And so in the main, I'm going to put down that it's the first regression model. All right, so here this looks like a typical regression model. Now these points aren't tight enough around the line for me to use this for prediction, but I could use this for inference. So a slope of 3 is something that might be interesting. That might be important if I was doing a real inference problem. Okay, now let's take a look at the second one. Huh, I got like this curve. It kind of looks like, you know, if I ignored the red line, I would say that looks a lot like a quadratic from college algebra. Now here is the line of best fit. Now, does this line like really look like it's matching up with the data points? No, it doesn't. So one thing we want to do is whenever I start looking at stuff, I don't want to see a pattern that my model doesn't pick up. I see a curve, but my straight line model does not pick up a curve. So I have concerns about this model. I wouldn't want to use this. All right, let's look at the next one. So check this out. So, what did I, there we go. I've got like this line of points. So just focus on the line of points right here. That looks like a good, nice line. That's a beautiful line. Is that the line my model gave me? No, no, it's not. It's close, but it's not. There is a difference. We can see that this line is kind of moving off on us. It's a little bit different from it. It's not too far off, but it is off. I mean, if I look at these points, all of these points, if I ignore the one up here, ignore this, if I go along this, I can see that it should be a perfect line. But my model is not a perfect line. There's a problem. This one point is so far off from everything else that one point is pulling the entire model away from all of these. Now, something that you want to use as a rule of thumb when you're looking at these plots, if you were to take one point and remove it, or if you take one point and move it around, and if you see visually in your mind, you see like something different going on in your data, you probably can't trust what's going on. If you can move one point, delete one point, add one point to your scatter plot, and that visually changes what's going on, then you don't really want to trust that model. That's something that's a good rule of thumb. And so when we have like small data situations, we have to be more aware of the impact of one data point on the rest. So here, this looks like this might be an outlier. This might be an error. This might, maybe the X value was recorded incorrectly. Maybe the X value is way over here. It would be the correct one. Or maybe the Y value was incorrect and it should be down here. Maybe both of them are wrong and the actual point would have been down here or something like that. We don't know. Well, it's a fake data set anyway, so we won't know anyway. So, one of the takeaways from this is that one data point, when I have small data, can pull everything off. Well, okay, people always say, oh, well, small data, it's not as interesting as big data. Big data is sexy, and you see, these big symposiums and people talking about it. Well, something about the explosion of data in our modern society is that this has made like small pockets of data more important. So when I get into nuanced specific problems, I'm going to fundamentally be working in small data. So with the explosion of big data, actually small data has become a lot more important. Now, why would I be in a situation where I only have a few data points? Well, maybe we only have a few. Maybe it's very expensive to get one data point. If it's expensive to get one data point, I might only have, this much to work with, and I need to come up with an inference. Well, if I'm in that situation, I need to know what can go wrong so I can protect myself. Now, if I have millions of data points and I can trust the data collection process, I don't really have to worry about much. But, I'm not being paid to worry about the easy situations. I'm getting paid to worry about the difficult and the problematic situations. So we need to be very aware of this phenomenon where one data point can throw off the entire results. Okay, let's look at another situation. All right, well, here, all of our data, except for one, is in this one spot. We have the same X value for all of these, and then we have an X value that's different and a Y value that's very, much greater than the rest. So what's going on is if I was to get rid of this one point, if I was to cover it up, what would happen is that this model would actually be a flat line passing through the average of these ones. So this would be a constant slope 0 model, just passing through the average of here. The y-intercept would be the average of the x of the y values. So this one data point made it from just being an average to being a linear regression problem. So then we have to go, do I trust this? Is this a mistake? Maybe we had like a sampling system that did not include very many points outside this. Maybe this X value is rare in the population. We don't know. We would have to dig in. But as is, if you handed me this, I would not feel comfortable using this point over here in the data set. And frankly, I wouldn't use a regression model because I'm largely basing this off of one data point to control what is the slope. If I'm using one data point to tell me what the slope, remember, a line passes through 2 points. So we've got the x coordinate, and the average of the y's is this point here. And then this point over here is the other point. That's 2. So x coordinate, average y's, first data point, or first point on the line. And then this point over here is my second. Those 2 locations dictate everything about this line. That tells me the y-intercept, that tells me the slope. Well, that's a lot to, that's really effectively this thing. If there's any error on this, error on the x values, error on the y values, a mistake was made, sensor wasn't working right, anything like that, that could have a big impact on this model, and I'm very vulnerable to making a mistake. So I need to, this point is absolutely critical to being correct. So if I was working on a project and you handed me this data set, first thing I would do, I'd be like, hey, I need to know about your sampling scheme. I need to know about how you designed this, what you did, what is going on with this point. Tell me everything about this point here. If there's any problems, I have to say, I can't work with it. I cannot give you a reliable inference. And now what to do employment-wise when you're in that situation, it's gonna, you just have to have some tough conversations. Now let's look at the residual. So what will actually end up happening when we get into more predictor variables, when we're doing multiple linear regression, it's going to be a lot harder to look at individual variable scatter plots. So if I have 5 predictor variables and 1 target variable, I'm going to have a lot of scatter plots to work through. In that situation, it's harder to wade through it. So what we end up doing, we end up plotting the residuals, and that's really a better way to approach it. So the residuals are the error between my model and the predicted value. All right, so you'll notice, remember what did I say about what do the residuals add up to? They add up to 0, therefore the mean is 0. And you can see that if I put a regression line through these points, the regression line is going to be a flat 0 y-intercept line. And so I don't see a pattern. If I was to take one point and move it or delete it, add a point, I wouldn't visually change the model. So this looks like a good model to me. Now, the residuals are big enough for the size of the data that I'm working with that I wouldn't trust this for prediction, but I could use this model for inference. So the first model, I'm okay with for using it for inference if this is what I was seeing in real life. Now let's go down here. So a rule of thumb, when I'm looking at my residuals, if I see a pattern, then that's a problem. Now, how to handle that problem, that's a very big topic of conversation. But for now, basically, if you see a pattern in your residuals, you know to pump the brakes. I look here, and I see that I've got this curve going on. Now, you'll notice that if I add up all of the y values on the residuals, then they're going to add up to 0. They're going to be mean 0, and that's how I get this line. This is the line of best fit on this data set. It is a flat 0. All right, well, if I see a pattern, I have a problem. So here, to correct that, I would want to add a degree 2 term to this model, is how I would approach this. Now the next one, once again, I see a pattern in my residuals. So I see a pattern in my residuals, I pump the brakes. So I see this line going on here, and then this one point floating out on its own. So I know that there's something off, something is wrong. I do not want to launch this model. Now, last but not least, I can see that it's just going, flat like this, and it's a perfect fit through that one point. So remember that if I only have 2 points, then that determines a line. 2 points determine a line from your college algebra days. This is one of the points, and it's passing through the average of these y values. And so since it's passing through this point, it's automatically going to fit through this one particular point. This point has a lot of influence on this model. So I have to either have a lot of trust in it, or I need to pump the brakes. All right, that's all I've got for you. I hope you're doing well and staying safe. Goodbye.